Hi everyone, today we're going to be talking about designing distributed key value storage, for example like Redis. First of all, let's make sure that we have a right place for our storage to put him in. Right, we have some user. We have several users that's going to be querying our service. Let's say, for example, we are marketplace. Okay. Of course, we have some kind of storage. It can be, for example, PostgreSQL or maybe Amazon DynamoDB or some kind of graph database, whatever it is. It has always have limits in terms of high latency comparing to accessing data that is in RAM. So in order to lower this latency, typically what's used is cache. And cache is often implemented as a key value storage. For example, Redis, of course. All right, so basically we have cache. And this is, of course, our today's topic. Let's talk about this part where cache come into place, what it is, how it works, and so on. So now let's go to the next section and discuss requirements. Now let's talk about requirements. First of all, let's discuss functional requirements. We want to be able to put some data in our key value storage. So key value storage. Of course, we want also to extract or get some data from it. And also we want to control an eviction policy. Basically some algorithm how we're going to be cleaning data from a cache or key value storage. Set eviction policy. Okay, I think it's sufficient for our video. All right, moving on to non-functional ones. First of all, let's be performance, because cache is all about speed and delivering results. Availability. This allows us to be fast a lot of times, most of the time. And of course scalability, because we talk about distributed cache and of course systems that have a high load. I guess that will be it. Now let's move on to general system design. But now let's talk about the foundations of our system design. First of all, let's discuss fundamental data structures for key value storage. This will be hash map for storing data and double linked list for storing ordering of hash map keys. This ordering depends on our eviction policy, and let's for now focus on LRU, and also means list recently used. All right, now let's discuss how we're going to be satisfying our functional requirements using these structures. Let's talk about interactions with our user. So as discussed above, we must deliver on two methods per requirements. This will be get and put. First of all, let's talk about get method. So basically I want to get some item 1. If we don't find it in our key value storage, then we return none. And if we do found it, we firstly put item 1 to head of double linked list as per our eviction policy list recently used, because we must always update if any item got touched, update it to head of list, and return item 1 to user. All right. In case of put, we firstly need to assess if we have enough space available, and if we have space to put another item. We firstly check if maybe we already have a key that is proposed to us with value, and if we do, we update value of key to new one, and if we don't have key, then we add item 2 to hash map. And also, of course, we add item 2 to head of double linked list. Now, in scenario where our cache is full, so basically we cannot hold any more data, we firstly remove item which is located at tail of double linked list. This is like per our policy, of course. And then we remove this item from hash map. And we perform steps of cache have space scenario. All right, now let's talk about other eviction policies. So for example, we can talk about least frequently used. This will require us to keep some frequency counter, least frequently used. For example, we might put in our double linked list counter for every item, and this will allow us to understand which item is hot or like mostly desired by our users, and we will not allow it to be removed, even if it's not asked recently. So for other policies, you can deduct the same logic. All right, now let's move on to the next part. We covered fundamentals. We may move to distributed key value storage. Of course, you can scale cache vertically, but at some point you will be out of RAM generally available, or say, for example, it will cost too much. So you need to go to other technique called sharding. Basically, say we have at our marketplace a lot of data points, let's say users for simplicity, and say we are going to be sharding by user ID. Basically, some users will go to our first cache, some to second, and some to third, depending on their ID. What that means is that we're going to be using a hash function applied on our key. That's going to be, say, in our example, it can be a user ID plus maybe name. Like, say, for example, we want to store ID to name mapping on every cache, but it's just like for simplicity. And now that we have taken cache of our key, which is like user ID maybe, we can use such simple assignment function as a module of 3, because we have 3 servers. So basically, let's ID them as 0, 1, and 2. Basically, when we have 0 is case, for example, where our cache function returned any multiplier of 3 and 0, like hash function 0 will give you 0, hash function result of 1 will give you 1, and this item will go here. Hash function of 2 will give you this one, and this will go here. Hash function of 3 will give you again this one, so let's go to this server. So basically, this is how you distribute your user IDs mappings to different caches. All right, now let's discuss drawbacks of such a simple function. All right, now let's talk about drawbacks. So everything's working great. We have our 3 caches, data flows, everything good. None of them is, say, go down for at least a long period of time. But we are scaling up and we need another cache. So let's just add this one and assign him ID 4 to it. All right, great. In order to allow flow of data from this one to here, we need to change this assignment function, because currently we only have 3 options for our user ID. All right, let's update it to mode 4. But upon updating this to a new assignment function, we have a problem. Now some of keys that were stored here, here, and here are going to be moved to ID number 4. And what this creates is a problem to some period of time, because user asked for some key, and previously it was stored here, but now hash function is assign you this key to ID 4, and marketplace goes for this key to cache 4, but cache 4 was just added, so it has 0 keys available. And basically what we have is missing key. So we return with none. Alright, and also now our 3 caches store irrelevant data, which never will be accessed, because marketplace can only go to where hash function maps him. Alright, that's pretty problematic, because you would need to wait invalidation of many keys from these 3 IDs, and also filling up this cache with not new keys, but with old keys from them all. Alright, now let's discuss how we can tackle this problem. So basically, we have 2 sides of problems. Firstly, we add some new cache service, or we remove some cache service, and this creates a problem of redistribution of keys, invalidation, and like load distribution and so on. Alright, so to solve this problem, we will introduce a circle which will represent IDs, or maybe hash result IDs, something like this. Basically, you apply hash function and you get a number which will be mapped to some point on this circle. Alright, first of all, we need to present where our caches will be on this circle. So let's say we have some cache 1 and it got mapped here. We get ourselves cache 2 and it got mapped somewhere here, cache 3 somewhere here, and cache 4 maybe somewhere here. Yeah. Alright, how we mapped is pretty up to you to decide, but basically you need to assign for every cache server you have some unique value. It can be IP address or maybe some name of this service which is unique, and then you apply hash function which will map this to some number. Alright, now we have distributed our servers, and then say we have some key, oh maybe value key, yeah, key 1, which we want to like decide in to which cache we're gonna keep it, or maybe some item, I would say. We want to put some item into any of the servers, and to decide this we also apply same hash function on this item and get some number. Let's say item got somewhere here. Alright, how about we have some another item, item 2. We also apply and it got somewhere here. Okay, now we decide that we will be moving from item clockwisely, or counterclockwisely, not really important, but just decide on one. Say we're going to be talking about clockwisely. So okay, we are moving clockwisely and assigning item to server which met first. So item 1 will be moving clockwisely and will meet cache 2 first. Item 2 will be moving clockwisely and firstly meet cache 4. So basically, this logic allows you to distribute items towards cache servers. Of course, you can see that our cache servers are not equally allocated. Like the space, the number of IDs they cover are not equal, because C4 have like the smallest number of IDs available. C3 have, I think, the most. Yeah, it seems like this. Oh, sorry, C2 has the most available. C3 and C1 about equal, so it looks okay. In order to deal with such a problem, you would need to create what's called virtual nodes. So basically, we have our caches, and we assign them extra like naming maybe, so we can add something to IP address or whatever, and we will get another copy of C4, well, let's say here, let's say maybe here, and I guess 3 is sufficient, and they will be like different names. So for example, C41, and we need to embed case of mapping, okay. But general idea hopefully will be clear. All right, so basically those three numbers on this circle map you to the same server, but this allows you to equally distribute. So for now, C4 covers this line, and this line. We of course do this procedure for every server. So basically we may put something office tree right here and say here, and same goes for other servers. So now you have efficiently created virtual nodes on different points of circle. This will allow us to equally distribute the load to different caches. Because the more also we can have arbitrary many virtual nodes, but you need to be aware that for storing them you need to allocate some space, you need to be to like consider them when removing something and so on and so forth. But generally you can keep some arbitrary number, let's say 100 of virtual nodes, which will accompany 4 real nodes, real caches. And this will allow us to solve problem because we remove, say, C3 and many virtual nodes of different, like C2, C1, C4 may even have some node, will somewhat equally redistribute load between them. All right, so basically that's it on consistent hashing. Now let's move on to next topic. We'll discuss data replication. We sharded our data onto different caches, and everything is good and okay until the moment some of our servers fail due to some natural disaster or hardware failure or maybe some software troubles. Whatever this is, in order to be highly available, we would need to replicate our data and best of all replicate to different clusters. So say for example, we will use a model of leader-follower or master-slave. So we have some cache that is assigned as leader, and we have several replicas of this leader or followers. Let's say we have 3 followers 3, follower 2, and follower 1. So reviewing our requests, we can have some put and get request. So for get request, we can go straight to some follower. All right, good. And for some for put request, we only go to leader. So leader is our only point where we can write something into our key value storage. Right, let's make it somewhat wiggly. To be right here. All right, and say again, it's our lovely marketplace. It's coming into place. Marketplace. All right. Great. Of course, an arrow to the leader. So let's say this one get and put. It covers both, and other will only cover our put request. Oh, sorry, our get requests. Okay. So what this makes, let's make sure that maybe we have some, say, different clusters. I'm not sure, maybe to go in red, like say this is EU West. Say for example, this is US. Say for example, US West, and say for example US East. Right. So okay, and this will be, let's say, again, Euro Central, for example. All right, generally we have different clusters which allow us to be prepared in case if some of the cluster will go down. Say for example, US cluster got cut off and we have other replicas and we have our leader available. In situation where our leader got down, there is a choice between some of the followers will be chosen as leader, and then it will get put requests instead of our leader. All right. That's, I guess, covers data replication. Now let's move on to the next section. So for putting and getting data, we have discussed hash map, which is used as underlying data structure for our key value storage. About setting eviction policy, we discussed least frequently used and least recently used policies. So for least frequently used, you also need to add counter in order to make sure that you count number of requests for different items and sort them accordingly. So basically, you will need in your key value storage to have these implementations, and then you can just allow users to send you a request of setting a certain policy, and you will just like use your implementation which suits chosen eviction policy. All right, for non-functional requirements performance, as discussed, caches and our key value storage case of using cache will be highly utilizing RAM, which allows the fastest possible access to data. This covers performance. For availability, we have data replication. This allows us to send get requests to many replicas, and generally cache is most used for getting data. So basically you need to have a lot of read replicas. For scalability, we discussed sharding and utilizing consistent hashing for this to equally distribute put and get requests between shards. All right, I think this is it. So click follow and set likes. Thank you so much for watching, and goodbye.